Let's look at the reactivity of carboxylic acid derivatives, and I will first draw these in order of decreasing reactivity. Where the acid chloride, and actually you can make acid bromides too. We don't see them very often because they're actually more reactive than the acid chloride. And as we'll find out in this chapter, the acid chloride is certainly reactive enough for our purposes. Then we go to the anhydride, the ester, and the amide as the least reactive of these four. So we can determine their level of reactivity by running reactions and comparing them. And then we can support that outcome via resonance. So let's look at the resonance of the acid chloride. And we know that every carbonyl species has a pi bond between two differing electronegativity elements. And so we can draw the pi bond moving on to the O like this. That gives us to this resonance structure, and then of course we do have some lone pairs on the chlorine, which we could draw like that. I think that's probably not a very good resonance structure because that puts a positive charge on the highly electronegative element chlorine. Also, chlorine is a lot larger than a carbon, and so there's not very good overlap between the chlorine p orbitals and the carbon p orbitals. So this is a weak pi bond, a much weaker pi bond than this one or than a CC pi bond. So let's put our brackets around that. Those are the three resonance patterns we can draw for the acid chloride. So I want to put a red mark here. This is a poor contributor. And so that we see there's only really two resonance patterns. And we see that if these two resonance patterns are sort of melded together into a hybrid or average resonance structure, we don't have a lot of support or a lot of stabilization of the carbocation here. And we also know that the chlorine by itself, by induction, serves to withdraw electrons from the carbonyl carbon. And so the end of the day, the outcome here is that the chlorine effect is to withdraw electrons via induction. The chlorine itself does not really add any more resonance structures, therefore resonance stability, to our initial carbonyl compound. So really the only thing that the chlorine is doing in our acid chloride is to withdraw more electrons from the carbonyl carbon, making that a better electrophile than it was as a aldehyde or a ketone. Let's compare that with the amide resonance structures. And of course, our first resonance pattern is the same as everything else. There is a lone pair on the nitrogen, and I'm a lot happier using the lone pair on the nitrogen as a source of electrons to stabilize that central positive charge than I was using the lone pair on the chlorine. And so these are the three structures that the nitrogen or the amide will provide for us. And this one is a much more useful resonance structure than this one, because here I have a nitrogen which is less electronegative than chlorine, so it's less unhappy having this positive charge on it. It is in the same period as the carbon next to it. Therefore, the p orbitals on the carbon and the nitrogen should be of similar size, and they should overlap better in this case to provide a stronger pi bond here. So this resonance structure that I drew here, and I'll underline it, the third one, is actually very useful. So this has good overlap. This is a good contributor. So now, instead of two good resonance structures and one really sort of okay resonance structure, I have three decent resonance structures, and they can all combine to give me the overall picture of the electronics in the amide structure. And thus, at the end of the day, the N stabilizes the carbonyl carbon. And so you see that we got a decrease in stabilization from the electron withdrawing chlorine. It didn't contribute any useful resonance structures to us. And over here with the amide, we got an increase in stabilization due to this third useful resonance structure. And so that's a big argument for the order of reactivity here. As you go from the chlorine to the acyl group to the OR to the nitrogen, we're getting a little more stabilization in that third resonance structure.